thanks for watching. And today we'll do something that's extremely important in PDEs. We will use energy methods to show that there's at most one solution for the wave equation. Because the setting is as follows. Suppose you want to solve UTT equals c squared uxx with initial condition phi of x and initial velocity psi of x. Then we know that one solution of this is given by D'Alembert's formula, which is 1/2 phi of x minus ct plus phi of x plus ct plus 1/2c integral from x minus ct to x plus ct of psi of s ds. And the question is this the only solution of the PDE? Or in other words, are there other solutions? Other solutions. Or in other words, if your friend solves that equation, will they find another solution? And the cool thing is, the answer is no. We will show today that this is legitimately the only solution of this PDE. And you'll see this is a nice application of the energy method. And for this, we need to show a first lemma, because if life gives you lemmas, make lemonade. So lemma. Let's take a slightly easier situation. So suppose W solves the wave equation. So WTT equals c squared WXX, but this time with 0 initial conditions. So WX0 is 0 and WTX0 is 0. In other words, suppose you have a wave and initially, so at time t equals 0, the wave doesn't move and the velocity is also 0. Then what happens to the wave? Well, then we will show that Wxt is 0. So if you start with a 0 wave and it doesn't move, then the wave is always 0. And for this, we need to use the energy methods from the previous video. Because once again, define the energy. So let E of t to be 1/2 integral from minus infinity to infinity of Wt squared plus c squared Wx squared dx. And last time we've shown that E is constant. So check out the previous video. And we have legitimately shown that E of t is constant. And now, because this energy is constant, it always has the same value, and in particular, E of t is the same thing as the initial value, E of 0. So just by analogy, if I tell you the weather is always the same, then the weather next Sunday is the same thing as the weather today. So in particular, the energy at time t is the same as the energy now, which is the energy at 0. So once again, in particular, E of t is E of 0. And so let's write this down in terms of our formula. So 1/2 integral from minus infinity to infinity of Wt xt squared plus c squared Wx xt squared dx is the same thing as 1/2 integral from minus infinity to infinity of wt x0 squared plus c squared wx x0 squared dx. And here is, well, we need to use our assumptions. So this wtx0, by assumption it is 0. So but, again, wtx0 is 0. And also, it turns out this is 0 just by using the initial condition, which technically is a function of x, and differentiating this. So then wx0 with respect to x is 0x. And so what we get is wx at time 0 is 0. So just to give you a little analogy, let's say if initially the initial condition is x squared, then in fact the derivative of this would be 2x. Except instead of x squared we have 0. So we're literally differentiating 0 with respect to x. And that's very good because now we know that the right hand side, this whole shebang, is just 0. So in other words, the energy itself is always 0. And that's extremely important here. So now what have we found? We found that 1/2 integral of wt xt squared plus c squared wx xt squared dx is 0. And the problem is there's some pesky integrals. We kind of want to get rid of this. But notice what we have. We have the integral here of a positive function. So the inside here is positive, and I'm telling you that the area under this positive function is actually 0. So we have a function above the x-axis whose area is 0. Well, the only way this can happen is if that function itself is 0. So once again, a positive function with a 0 area is 0. And therefore what we get, wtxt squared plus c squared wx xt squared is 0. And even more than that, notice this is just a sum of squares. So each of those is non-negative, like this. And the only way the sum of squares is 0 is if each of those individual things is 0. And so what we know is wtxt is 0 and wx xt is 0. So in other words, what do we know about w? It doesn't depend on t, because the t derivative is 0. It doesn't depend on x, because the x derivative is 0. So it doesn't depend on either x or t, and therefore it is constant. It is constant. So in other words, w never changes, but remember, initially w is 0, and so the constant is 0. So C in this case, you can plug in t equals 0. And remember, assumption is 0, and so C is 0, which tells you ultimately that our function w is 0. So once again, slightly obvious statement, but with a very delicate proof. And now the cool thing is, we can now use this lemma to show uniqueness of the wave equation. So now let's prove the théorème du jour. So fact, there is at most one solution to UTT is c squared uxx with initial condition phi and initial velocity psi. Meaning that there's either 0 or 1 solution, but in this case there is exactly one solution because of D'Alembert. So what do we need to show here? Well, all we need to show is that if you find a solution and your friend finds a solution, then both of you should get the same answer. In other words, let U and V be two solutions of the equation above, and ultimately we want to show that U equals V. This is what it means to have at most one solution, or to prove uniqueness. So very, very important. Now, in this case, we want to use an extremely standard trick for showing uniqueness. Namely, let's consider the difference between two solutions. So, trick. Let W be U minus V. And let's figure out what PDE W solves. So then, first of all, WTT, that is U minus V TT. So that's UTT minus VTT. But U and V solve the wave equation. So it's c squared uxx minus c squared vxx. So that's c squared u minus vxx, which is c squared wxx. So that's already good. W solves the wave equation. And now let's just plug in the initial conditions. Then, second of all, Wx0. Once again, W is U minus V, so it's Ux0 minus Vx0. But once again, U and V solve the same PDE with the same initial condition. So it's phi of x minus phi of x, which is 0. And last but not least, WTx0, that is UTx0 minus VTx0, but that's psi of x minus psi of x, and that's 0. So ultimately, what does W solve? So then W solves literally the wave equation. WTT is c squared wxx, but with 0 initial conditions. Which, by the way, makes sense physically, because if two waves start at the same place, well, their difference should be 0, at least initially. But notice, this is precisely the situation of the lemma. So by the lemma, we know that if you start with 0 position and 0 velocity, you are the 0 wave. You are the moment. But now, remember, W is U minus V. So U of xt minus V of xt is 0. And that's precisely what we wanted to show. Because now we've literally shown that U equals V. So from now on, you can sleep in peace knowing that there is exactly one solution of the wave equation given the one by D'Alembert's formula. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.